Okay, so welcome to firmware training week 3. I just hurt my knee. Anyway, so last week we did some C++. We got absent state machine, and then this week we're gonna see register and timers, PWM, binary and hexadecimal, bitwise operations, masking, and then you're gonna do the lab. So just a first reminder right now, please pay your dues. They're due Saturday at October 10th. You can do that on that link, at that link, and in general, you can just ask your PMs or core officers about it. Okay, so registers and timers. So what is a register? A register is a hardware used to read and write multiple bits at once. We use it for memory to store information. Microcontrollers often use registers to control the function of various parts of the device. And methods like Arduino's digital write modify the value of a register that controls whether a pin is high or low. So if you want your microcontroller is going to talk directly to your chip, and the way it does that is that you just send an instruction to some specific register, and then this register is going to say, hey, I want you to be pretty much a 1 or 0, right? And then in function of that, that's going to help you actually do stuff. Timers and timers registers. Timers are a peripheral device used to count up to a certain value before resetting. The timer registers are registers that act as timer, and they can be used to trigger different actions at set intervals by checking the value of the timers, a register against a different register. So if you want, you can use them to actually even to trigger interrupts, right? Like we did in last week's lab, so that you can actually do something about it. Yeah, timer registers are cool and useful. PWM. So PWM, I am struggling so hard with this word, means pulse width modulation. So the way it works is you alternate between a low and high voltage. Wait, let me see if I can. Okay, I can actually point. Okay, so by alternating between a low and high voltage, the effect of the middle voltage can be achieved. So by varying the duty cycle of this alternation, the spectrum of voltage between the low and high can be between the low and the high value can be analyzed. So if you want the way. So usually we use it, for example, for motors or other stuff, right? But the way a PWM works, right, is you will be able to achieve, for the motor example, right, a different speed in function of how you vary your signal, but with the same amount of voltage coming in. So with just the same voltage coming in, right, imagine you have 5 volts coming in. By varying your duty cycle, so your pulses, right, you're going to have a different middle value, and this is how you're going to achieve like a different speed for your motor, right? So here you can see you have 25% duty cycle. The average is lower than if you had a 70% duty cycle. Yeah. Now, relation to timers. So you can also use PWM for timers, and then if you by switching the frequency, switching frequency is controlled by a timer register, and then the time voltage is high compared to the total time tells the percent duty cycle, which directly relates to the output voltage. So this is a triangle wave timer register, if I remember well. But I just stopped. Anyway, so this is how actually you get the switch in frequency for what you're doing. Binary and hexadecimal. So what are binary and hexadecimal? Those are alternate number systems. So if you want, the way we count is we count base 10, right? We count with the numbers 0 through 9. We do all of our regular operations with those. However, there's like, you could count, and so that's base 10, right? But you could count in as many bases as you would like. If you wanted to count in base 4, you could, or base 36, right? And so now we're focusing on two different like different bases that we actually use in to code in general in firmware, right? And so one of them is binary, so it's base 2, and so the way you count is with 0 and 1, right? And then hexadecimal is base 16, and so you go through the number 0, 9, and then because we don't have single-digit numbers for later in our like regular base 10, right? We now put letters, so 10 through 15 will be A through F. In general, so the way you do, right, is like you count like in any other base system. So for example, in base 10, right, we do 0, 1, 2, etc. through 9, and then at 9, you use a 1 and then a 0, right? So it's like if you start it all over again, right? Well, in binary, it's the same, right? You do 0, 1, right? But then because you don't have all of those numbers, you go to 10 directly, right? And then 11, and then now you don't have other 0 and 1, so then you go to 100, and then 101, etc. You can see the list on the side, right? And for hexadecimal, right, you go through 15, right, which will be F, but then 16, right, will be 10 because you go back to the start again, right? Okay, so now we're gonna go through a couple examples on how you convert from binary to decimal, decimal to binary, and then hexadecimal to decimal, decimal to hexadecimal, and then binary to hexadecimal. So first, decimal to binary. So here we're using the example of 158. So 158 in binary is this number. And so the way you go from 158 to this number is by doing a bunch of divisions by 2. And then your binary is actually going to be your reminders going from the last divisions you did to the first one. So 158 divided by 2, right? It's 79. So your reminder is going to be 0. So you do all of these calculations until you're at like, whoops, now I can see the last thing because of slide 13. But anyway, to the last operation, which is 1 divided by 2, and that will give you 0 with a reminder of 1, right? And so now your new to get your binary number, right? You will go from that like last result, which is 1, the reminder 1 from 1 divided by 2, and then you go upwards. So now your number will be 1, 0, 0, 1, 1, 1, 1, 0, which you can see up there. And now to go from binary to decimal, if you have your binary number, what you're going to do is that you're going to put some, you can see this little table that you have like powers of 2, right? And so 2 to the power 0 is 1, etc. You go, right? And so to get to that number, you just like plug it in a sense, right? You just like put your binary, and then you see that like you just have to add those, right? So right now I didn't put the zeros here, but it's actually 128 times 1 plus 2, 64 times 0 plus 2, plus 32 times 0 plus 16 times 1 plus 8 times 1 plus 4 times 1 plus 2 times 1 plus 1 times 0. And this is how you get 158. Now conversions, the hexadecimal conversions. So decimal to hexadecimal is actually the same process, right? So you divide your, to still keep using 158, right? Well, now you're not going to divide it by 2 because we're not in base 2, but we're in base 16. So you're actually going to divide it by 16. And you're going to use your reminder again, and you're going to go from again, bottom to top, right? So 158 divided by 16 is 9. Then 9 divided by 16 will give you 0, but that's with both of your reminders, right? 14 and 9. And so again, as we saw in the previous slides, 14 is actually E. And so now your hexadecimal number that represents 158 is just 9E. And then to go from the hexadecimal to decimal, when you have 9E, right? So you're gonna do, you're gonna write 16 to the 0 is just 1, and then 16 to the power of 1 is just 16, right? And so you can just add them together. So you're gonna do 9 times 16 plus 14, and that will just give you 158. So it's exactly the same process as you had in binary, just like, I guess, more difficult divisions and multiplications. Now, conversion between hexadecimal and binary. Why do we use both of those in coding? It's like they're like, the way to go from one to the other is super easy. So actually, each number in hexa, or so in hexadecimal, right? You can represent every number in hexadecimal by just 4 bits, right? So if you see, look at the table right now that you can see, right? 9 is just gonna be 1,0,0,1, right? And then E is just 1,1,1,0. So this is the way you get from one to the other, and you can do the exact same thing. If you have like a gigantic binary number, right? If you cut every 4, right? Starting from the last part of the number, because sometimes the first zeros are gonna just be ignored, but by doing that, you will just get, you can just convert it directly to a number. So super easy. You just have to use pretty much a table. Okay, so now let's talk about bitwise operations. So bitwise operations, there's pretty much, I mean, there's a couple, right? But the ones we use the most are AND, OR, and XOR, which we're presenting right now. And so those are logical operations, but instead of comparing conditions like we saw with if, or like while, or like whatever, now, for example, if you have if condition 1 equal condition 2, this is pretty much the same thing, but now you compare bits, right? Which bits you can kind of consider it as true and false, if that makes sense, right? So now you can see in the table on the slide, right? You can see if you have 2 bits and you do AND in between them, what you will get, or XOR, right? So AND is pretty much you need to have both of those bits to be, if you want both of those conditions to be true, to be able to have a true statement out. So both of them needs to be 1 to have a 1 out. But anything else, every time you have a 0, that will just be a 0. OR is the exact opposite of an AND. You need at least a 1 to be able to get a 1 out. But if you have both 0, it's going to be a 0, right? And then XOR is called exclusive OR, which means you need to have actually a different value between your bit A and bit B. So, right, if you have 0 and 0, that will just output a 0 like the OR. But also if you have a 1 and 1, that's also going to output a 0 because it's not an exclusive OR. So now where you're going to get 1 is if you have 0 and 1 and 1 and 0. So here you have a bunch of examples with 67 and 42, which are those bit numbers, right? So here you have the AND, the ampersand, right? And you can see that the only thing that is going to output a 1, right, is just when you have 2 1s here, but everything else is just going to be 0. This is the OR, the bar, right? The OR, you can see that every time you will have a 1, at least in one of the columns, it will output a 1. So here, here, and then here. And even if you have 2 1s, you're also going to output a 1, right? And then if you have an exclusive OR here, you will see that it's only when you have a 1 and a 0 that you will output a 1, right? So in those two cases, and here as well, so pretty much like the OR, but the only thing that is different is here when you have the output, the 1 and 1 output, here you have a 0. So now another bitwise operation you can do is called a logical shift. So you have both, you have a left shift and a right shift. And so what does it do is if you have your number, so for example here you have a 10 in binary, so 2. You can see that if you shift it to the left, it's like if you were shifting your number like it's like if your number was just like moving one spot up, right? And so here you can see, like, for example, the 1 shifted to the left by 1. If you had a 2 here, it would just shift by 2, okay? And that's equivalent to a single left shift is to multiply by multiply a number by 2. Super quick, super nice. It's a super useful operation. And then the right shift is you can a right logical shift, because you have also one that we do not cover here, but the arithmetic right shift, which is a bit different. But a single right shift divides a number by 2, but you do discard the remainder. So if you see here, right, you're gonna shift it to a right by 1, but but anything that goes up to the on the left, right, it's just gonna be a 0. So even if you discarded a 1, you're just gonna get a 0 on the left side anyway, right? And so if you had a 4 here, right, like if you had 100, right, which is 4, you would get the same result here because it discards the remainder, right? So 6 and 7 will give the same result, 5 and 4, etc., etc. So they're useful because they're very efficient. They use a small memory. They use small memory usage, and they're used in embedded device socket programming, which is networking and cryptography. Networking in like intranet stuff, not like LinkedIn stuff, cryptography, etc., etc. So now we're going to talk about masking. Masking use the bitwise operations to access or set particular bits. So what you do is you read a value from a binary number, and then when you have that, if you mask with zeros, so if you do an operation with zeros, you're gonna ignore parts of your number. So it's really useful. We're gonna see an example why. And then you can also decide to write only specific bits to 1. And so to do that, you can use a bitwise OR for writing certain bits to set bits to 1. And then masking with 0, you use a bitwise end. So here we have examples. So when you mask with end, any number and 0 will give you 0, and any number with 1 leaves that number. So here you have a number, right? And then you want, let's say you want to keep only the values that where you put your ones for the end, right? And as you can see here, it will keep every value that has the 1 under it. So here it's going to be a 0, and then a 1 here, and then a 0 here. But all of the rest, because it's ended with 0, it's just going to be 0. And then when you mask with OR, any number and any number or 0 leaves that number, and any number or 1 leaves a 1. So here opposite. Here you're gonna want to set some specific bits to 1, and so you will get those values, right? But then anytime you have a 0, you're just gonna keep it. So here it's not changing anything, but for both of the ones here that you had in the previous operation, it's just going to set that bit to 1, and then you keep all of the other values. So why is it useful? So imagine you have an LED or a color, right? And then you want to change that color, right? So right now we have green, and the actual specific number of that green is 34EB98 in hexadecimal, which is the long binary number you're seeing right here. As you can see, we color-coded the binary, so it's easier for you guys to see. But any color is made of, for the pixels, right, is made of red, green, and blue. And so different amounts of blue, green, and red will give you a different color. And so imagine you want to know how much blue you have in this color already, right? Well, if you do that, you can mask with your you can mask with AND, right? And then you can just decide to do zeros anywhere else that is not blue. Sorry. And then you can just do zeros everywhere that is not blue, and then you can just put ones everywhere that you have blue. And then doing that, it will just make red and green completely zeros. But then for blue, it's gonna give you it's just gonna keep the number you had previously. So now you can just use that specific value. And then now let's say you want to add red to this specific blue color, which is just 98 in hexadecimal. So, well, that will give you a nice pink, or I guess somewhat of magenta, by just if you mask with an OR, right? So you don't want to add blue, but you want to keep the same amount of blue. So by just doing 0, you're going to keep the same amount of blue. You're also going to keep the same amount of green, but it was 0 anyway, right? But when you add a 1 everywhere, right, that will make you just have the maximum amount of red you can have because you're doing OR, right? If you wanted to just do maybe less red, but still add some red, right, you could have done like 1 0 1 0 1 0 1 0 here, right? And that will have given you a color with less red, but still you set some bits to red, therefore you're going to have more red. Wait, that was already in. So that was masking. So now our lab time. So what are we gonna do? So in general, in the lab, you're gonna read about Mega microcontroller, timer registers. You're also gonna see in comparison to the Monday Monday session, we also added some PWM information just so you get a bit better, you get it a bit better. And then what you're going to do is you're going to set up a fast PWM mode using the registers, and then you're going to write interrupts like last week for the buttons, and then you're going to, the goal is to vary the brightness of the LEDs using those buttons to change the PWM, right? Because you're varying the amount of voltage you're giving to the LEDs.